Hello everyone, my name is Ankit Bhardwaj and today we'll discuss the bias-variance trade-off. So this concept explains the tension between choosing models that are simple enough to avoid overfitting, yet flexible enough to capture meaningful patterns. Mastering this trade-off helps identify and build models that generalize well rather than just memorizing data. So let's take a look at the agenda of this 10-minute demo. So we'll start by discussing what bias and variance are, then define these error components plus the unavoidable irreducible error. We'll see how total error breaks down mathematically and use visual demonstrations to make the concepts concrete. After that, I will share some practical guidelines for reducing bias or variance. Finally, we'll wrap up with key takeaways. So, starting with the first slide, which is discussing types of prediction error. So in supervised learning, prediction error comes from three sources, starting with bias, which is the difference between a model's expected prediction and the true value. High bias often means our model is too simplistic and misses important patterns. Then moving on to second, which is variance, which is how much a model's predictions vary if we train it on different samples. High variance indicates oversensitivity to the training data. And lastly, there is the irreducible error, which stems from randomness or factors outside a feature set. So while bias and variance can be managed through modeling choices, irreducible error sets a lower bound on performance. So you can consider this to be the inherent noise in the data itself. Uh, Now, moving to the next slide, which is understanding bias. So, bias is formally defined as the expected prediction minus the true function value. So, a high bias model will make strong assumptions. For example, fitting a straight line to sinusoidal data, which which will lead to systematic underfitting. And this is something you can see in the diagram also. Conversely, low bias means the model can flexibly capture complex relationships but may require more parameters or features. So to reduce bias, we can choose richer models, introduce more informative features, or reduce regularization. Next, we will move to discussing the variance. So variance will measure how much predictions change when the training data changes. So a high variance model is very flexible. It will adapt to every nuance of the training set, including the noise, which can then lead to overfitting, which is a position where the model performs well on training data, but poorly on new data, which is this is something you can clearly see a position of overfitting in this diagram also, where it is over capturing the data by by creating a very uh, over-complexing path. So this leads to overfitting. The model performs well on training data, but poorly on new data. A low variance model is more stable. It will give similar predictions across samples, but it still might suffer from bias if it's too simple. So reducing variance can involve simplifying the model and selecting fewer features or adding regularization. So now we can move to error decomposition. So starting first with the formula itself, we can formalize total prediction error as mean squared error equals to bias squared plus variance plus irreducible error. So this irreducible error represents inherent noise we cannot eliminate. So this equation highlights the trade-off, which is lowering bias. A way to do that will be increasing model complexity. So lowering bias tends to raise variance and vice versa. So the goal is to strike a balance where the sum of bias square and variance can be minimized. Now, in this diagram, you can see the visual demonstrations where we have three fits on the same data set. Starting from the left, you have a degree 1 polynomial fitting a straight line. And you can notice how it misses the curvature, which has high bias and is a clear case of underfitting. In the middle, you have a degree 5 polynomial, which captures the sinusoidal pattern without excessive wiggles. It achieves a good balance of bias and variance. And finally, moving to the right, which is the degree 15 polynomial, which literally snakes through every point. It memorizes the noise and oscillates widely. So this is a classic case of high variance and overfitting. And finally, we can move to discussing about the training versus test error curve. So the diagram clearly shows, and this curve shows training and test errors versus model complexity. So as we can make models more complex, training error drops sharply, but test error only decreases until a point and then starts to rise again. So the minimum of the test curve is the optimal complexity where bias and variance are balanced. So tools like cross-validation will help us find this right spot in practice. And now moving to some practical guidelines uh, to counter this, starting with when bias is high, what steps can be taken? Starting with moving to a more complex model, such as increasing polynomial degree or using deeper neural networks. Second would be add informative features to better capture the underlying patterns. Third would be to reduce or remove regularization if it's constraining the model too much. Fourth would be considering gathering more training data to provide richer information. Then moving to when variance is high, and the steps that you can take would be starting with first, employ cross-validation to tune hyperparameters and detect overfitting. Second would be simplifying the model or select fewer features to curb complexity. Third would be to add L1 or L2 regularization to penalize large coefficients. Fourth would be use ensemble methods such as bagging or boosting to improve the generalization. And fifth, in case of neural networks, one can consider early stopping to prevent overfitting. Then we can move to the last slide and talk about the conclusion and takeaways from this session. So if we have to summarize this, bias and variance are two complementary sources of error. The bias-variance trade-off guides us in selecting models that will neither oversimplify nor overfit. Some of the practical techniques would be model choice, feature engineering, regularization, ensembling, and careful validation. Now, all these help us achieve the right balance of uh, bias and variance. By understanding and managing this trade-off, we can build models that capture the true signal in data while ignoring noise.